3.5 is called putting it all together. So it's taking everything we've done from this unit, putting it all together, but it also draws from things you've done in the past with regard to functions. There are only 2 examples, but they're super long. One, we are just analyzing a function, so determining some things about it, which we'll talk about. And then the next one is analyzing and sketching a function. So right into example 1. Example 1 is analyze a function. We're going to consider the function f of x, which equals x cubed plus 6x squared plus 9x. And some things that we're going to do is determine odd, even, or neither. So this is reaching back to a different course. We're remembering that this would mean that the function is symmetrical. So if it's even, it has a line of symmetry. That can only occur in even degreed functions. If it is odd, it has a point symmetry, and it has an axis of rotation. It can rotate around that point and have symmetry. That can only happen to odd degreed functions. So since we're working with an odd degreed function, we're going to check to see whether this thing is odd. Oh boy, open a brand new pack of markers and the red is destroyed. So if it's going to be odd, the property that it needs to satisfy is to be symmetrical about the origin. So f of negative x needs to be equal to negative f of x in order for the function to be what we used to call perfectly odd. The easiest one to do here is figure out first what negative f of x is. Basically, it just means you take every term from f of x and you change the sign. So you have negative x cubed minus 6x squared minus 9x. Now we're going to determine what happens when we put negative x into f of x everywhere we see an x. So we have x cubed, that becomes in brackets negative x cubed plus 6 times negative x squared plus 9 times negative x. When we simplify this, we get negative x cubed, 3 negative factors. So that looks good. Then we get negative x squared, that's a positive. Positive x times 6 is positive 6x squared. And this term is negative 9x. So they look really close, but we notice that the sign in here in our middle term is different. So it does not satisfy that property. Therefore, it is not odd or even. It is neither. Neither odd nor even. Okay, we don't need to test for even because it's not even an even degreed function. Second thing that we're going to do is determine domain of the function. So the domain of f of x, it's a cubic. There's no restrictions on the domain. So no restrictions. Therefore, x belongs to the set of real numbers. C says determine the intercepts. Intercepts. So we're going to be doing x and y intercepts. The y-intercept is pretty easy. There is no constant term in f of x. So the y-intercept happens where x is 0. Well, if x is 0, then this is 0 plus 0 plus 0. So the y-intercept is 0. This thing goes through 0, 0. It's not symmetrical about 0, 0, but it does go through 0, 0. For x-intercepts, x-intercepts occur where y is 0. So we're going to set our function equal to 0. 0 equals x cubed plus 6x squared plus 9x. And now we just solve for that. First thing, solving means factor it, find the values of x that will cause the statement to be true. First thing I notice is they all have a factor of x in them, so we can factor that out, leaving us with x squared plus 6x plus 9. And that is a perfect square trinomial, which factors to x plus 3 squared. X plus 3 times x plus 3, two factors of x plus 3. So our x-intercepts then are x equals 0. That comes from the factor of x in front, and x equals -3. And actually, if we're remembering, we know also what happens then at each of these, at this x-intercept, it's going to cross through from positive to negative or negative to positive. And at this 0, it's just going to touch the line at x equals -3 because it's a 0 of order 2. But we're going to learn that through using derivatives. I'm going to clear the board and do the last part on a fresh sheet. In D, we're going to classify the critical points, which means we need to find them, and then tell whether they're max or mins, and then intervals of increase and decrease, intervals of concavity, and locations of points of inflection. So we're talking about derivatives here. Step 1, we're going to determine first and second derivatives. What are we going to do? Classify critical points. Step 1, first and second derivatives. I left f of x up here, so we can just take the first derivative, f prime of x equals 3x plus 3x squared plus 12x plus 9. And then to determine the zeros of that, we just set it equal to 0. We can factor out the 3, leaving us with x squared plus 4x plus 3. And then the factors are x plus 3 and x plus 1, which tells us our zeros are x equals -3 and x equals -1. We're going to do the same thing for the second derivative. So we're going to find the second derivative and then factor it to find our other critical point. So f double prime of x, here's f prime of x, it's 3x squared, so that's 6x plus 12, and set it equal to 0. Factor at the same time. 6, factor out the 6, you get x plus 2, which tells you that x equals -2. What does that tell us? There may be a point of inflection here. Okay, these critical numbers here divide the domain into 3 intervals to talk about. So the intervals that we're talking about then would be, and maybe just doing it on a number line is easier, but we've got -3 here, we've got -1 here, and 0. So what we're talking about then in our 3 intervals is anything x less than -3. Here we have in between -3 and -1. and then the rest of the number line is x greater than -1. So those are our three intervals that we're going to be talking about, and basically what we want to do is we want to find the value of f prime of x in each of those intervals and the value of f double prime of x in each of those intervals so that we can see the intervals of increasing and decreasing and whether it's concave up or concave down. So first derivative gives us increasing, decreasing. Second derivative gives us is it concave up or concave down. So I'm going to deal with each interval. I'm going to do first and second derivative within each interval. So the first interval is x less than -3. Test value could be, so for x is less than -3, test value x equals -4. If we sub that into the first derivative, we get, I'll just copy it all out, 3 times -4 squared plus 12 times -4 plus 9. -4 squared is 16 times 3 is 48. Minus 48 plus 9. That gives us a value of +9. Okay, it's positive, so it is increasing. I'll write a concluding statement at the end once we do the double prime one. F double prime of -4, again, just sub it in. We've got 6 times -4 plus 12. That is -24 plus 12, that's -12. That is negative. So we are looking at something that is concave down. So, statement, since f prime of x is greater than 0 and f double prime of x is less than 0, the curve is increasing and concave down over this interval. Next one's a little bit shorter because we only have to look at the first derivative because we know the second derivative at -2 is 0. So the next one, for the interval between -3 and -1, we're going to take a test value, x equals -2. Notice that the test value we took is actually right in the middle of this interval, okay? And we know from our second derivative, having a 0 there, that it could be a point of inflection. So it's an interesting point right in the middle of that interval. Okay, all we need to do is sub it into the first derivative, f prime of -2, and I'm just going to do this mentally. So our first derivative is up here, and we're subbing -2 in. So -2 squared is 4, that's 12. 12 minus 24, that's -12. Plus 9, that's going to be -3. Okay, so the first derivative is less than 0, which means that we are decreasing in that interval. Since f prime of x is less than 0, decreasing. Over this interval. And again, since there may be a point of inflection in this interval at x equals -2, we can't say whether it's concave up or concave down because it might change. Okay, so far in this interval we have increasing and concave down. Here we have decreasing, and now we're going to look at what happens for x greater than -1. Test value 0. Test value x equals 0. We're going to sub it into f prime of x, in which case we're going to get 0, 0 plus 9, which is positive. And in the second derivative function, sub 0 in for x, we're going to get 0 plus 12, also positive. And I'm not going to write since and all that statement. I'm just going to say that it is increasing and concave up. Therefore, increasing, because the first derivative is positive, and second derivative is positive, means it's concave up. Concave up. So we have increasing, concave up. Which tells us, since to the left of our, so we had a possible point of inflection at x equals -2, and because it's concave down to the left and concave up to the right, then we know that there is a point of inflection at x equals -2. So this kind of solving things and calculating things, that part is done for now, other than classifying these points. But we do know just from looking at this that there is a point of inflection. So x equals -2 is a point of inflection. We're supposed to classify our points. So we found out that we have, from our first derivative, we have critical points at x equals -3 and x equals -1. From figuring that out, we know that at x equals -3, then we have a max, and at x equals -1, we have a minimum, and we can figure that out algebraically by using the second derivatives. So to determine, or to classify, let's say, to classify local extrema, use second derivative. So all we have to do is put in our second derivative, put -3 in, and put -1 in. When we put -3 in, we get -18 plus 12, that's -6, right? And when we put -1 in, we get -6 plus 12, that's +6. So this tells us, since this is f double prime here is less than 0, it's concave down at this point. Okay, so we have a local max. And since at -1, the second derivative is positive, we have a local min. Okay, that's everything that we were supposed to find out. I'm gonna fairly quickly just summarize it in a chart. So our intervals, we said, are x to the left of -3. We're going to find out what happens at x equals -3. Then we have x in between -3 and -1. Then we have x at -1, and we have x is greater than -1. Those are all our intervals. We had a test value for each of those areas. Our test value here was x equals -4. This is obviously x equals -3. This test value is x equals -2, x equals -1, and x equals 0. And then we determined some things about the value of f prime of x and about the second derivative of f of x. And that's going to be used to interpret things about the original function f of x. So at x equals -4, we determined that the first derivative was positive, the second derivative was negative. That told us that we were increasing and concave down. So that looks like this. Okay, that's what a curve, this is increasing and concave down. This interval looks like this kind of curve. At x equals -3, the first derivative was 0. That's how we knew it was a max or a min, because the slope was 0. The second derivative was negative. That's what told us that it was going to be a local max. Local max. So that part looks like that. Boom, right there. In between -3 and -1, we found out that the first derivative was negative. The second derivative was 0. That's what told us it could be a point of inflection. And just to give us some context, this guy is going to be positive. So because the second derivative has a sign change at this point, that told us that it was a point of inflection. And we also know that the slope at that point is negative, so it's decreasing. The function itself is decreasing. And there is a point of inflection, not to be confused with point of intersection. So it's going to be decreasing with a point of inflection. So it's going to be coming off of -3, which is its max point of inflection, and coming down here to the local minimum. So right there is what's happening at -2. Then for -1, the first derivative was 0. That's how we found out it was a critical point. The second derivative is positive. That tells us that it is a local min. Local min, which means it looks like this. It's right there, coming off of our inflection point down into the -1, and then it's going to be coming back up, which is what's happening in the last interval to the right of -1. Our test value was 0. The first derivative was positive, and the second derivative is positive. So we are increasing at an increasing rate. So we're increasing and concave up. It's not right from there. So from here, you could actually draw a really good sketch of this thing. You know all of the key points. You'd have to find out the corresponding y values that go with each critical point and the point of inflection. And then also the zeros of the original function for where it crosses the x-axis. And that's actually what we're going to do in the next example, which is long and tedious and is going to take probably 4 pages. Okay, steps to sketch a full graph of a complicated function, polynomial function. Steps to sketch a graph of polynomial function y equals f of x. We already did a bunch of these steps in the first example. We're going to do them all in the second example. These come right out of your book, so if you don't want to copy them, don't worry about it. First thing, determine domain of the original function. Second step, determine intercepts. If you have the x and y intercepts of the original function, then you have a pretty good gauge on the drawing already. You just won't know the local max and mins. So that's the next part, is determine and classify. Determine and classify critical numbers. So that's first derivative work and some second derivative work. Then determine points of inflection. That's some second derivative work. Use that to determine intervals of increase, decrease, and intervals of concave up, concave down. So increase, decrease, concave up, concave down. So you can see we're going to be solving a bunch of equations in order to find the intercepts, first of all. So we'll be solving the original function. Then we're going to take the first derivative and then solve that to find critical numbers. Then we're going to take the second derivative and solve that to find points of inflection. Then we're going to talk about all of it and put it into a sketch, following these steps. Example 2, analyze and sketch. Here is our function. F of x equals x to the power of 4 minus 5x cubed plus x squared plus 21x minus 18. All right. Step 1, determine the domain. You have the steps written, so I'm not going to write the step each time, but maybe I'll just go like step 1 here. Determine the domain. Polynomial function, it's defined for all values of x, so domain is x belongs to a set of real numbers. Step 2, determine the intercepts of the function. Y-intercept is pretty easy. The y-intercept is negative 18. The x-intercepts, x-ints, occur where f of x equals 0. So what do? We need to factor this whole thing in order to find out the values of x that will actually cause it to equal 0. Do you remember some of the strategies that help us factor? How do I find my first factor? Because I can't use long division on this until I get a factor.
We're gonna do the division thing that we did like in advanced one. Yep, we are.
Yep, we really are. A couple times. Anyway,
Right.
here it goes. We're using the factor theorem. So the factor theorem says that if I sub a value in here and it comes out as 0, then x minus that is a factor. Okay, so factor theorem, factor theorem, if f of x equals 0, let's not do f of x, that doesn't make any sense. If f of a equals 0, comma, then x minus a is a factor. Helpful reminder. We are going to try x equals 1. And for the sake of saving time, that's 1 minus 5 plus 1 plus 21 minus 18. Yay, it equals 0. Okay, so that tells us that x minus 1, so x minus 1 is a factor. So I'm going to do this first step with long division. Then we're going to use some synthetic division on the next division. But to reach back, we are taking, and I'll do this in a different color to set this up, we put the factor that we found on the outside, and we put our original function under the long division symbol here. So we've got x to the power 4 minus 5x cubed plus x squared plus 21x minus 18. Be super careful every time you're copying a polynomial like that so that you don't miss things. And what do we have to do? We have to say how many x's go into x to the power of 4. It's going to be x cubed, and we're going to print that above our x cubed column. So we've got x cubed there. Now we're going to multiply back down around. Okay, so we have x cubed times x, which is x to the power of 4. X cubed times negative 1, which is negative x cubed. Now we subtract. These guys are 0, of course, that's how we got this term. Negative 5 minus negative 1, that's negative 5 plus 1, which is negative 4x cubed. Then just like in regular long division, we're going to pull down our next term, and then we're back at the start. How many times does x go into negative 4x cubed? Well, the numerical factor we need is negative 4, and the variable factor is x squared. Multiply it back down, we get negative 4x cubed plus 4x squared. Negative times a negative. We're going to subtract this down again. We end up with x squared minus 4x squared. That's going to be negative 3x squared. Pull down our next term. See if you can finish it on your own, and then just double check the board when you're done. And if you do it correct, you should get a 0 at the bottom. There shouldn't be a remainder. If this actually is a factor, there shouldn't be a remainder. That's what the factor theorem tells us. Okay? So we found one factor, and this is the other factor up here. But this obviously can be split up into more factors again. So what you would do is you would repeat factor theorem because it's still a cubic and because there is no common factor across the polynomial. You would use the factor theorem again for this this polynomial. Okay, so I'm just going to do it off to the side in order to save some space. I'm going to say I'm going to take this guy, factor theorem again, and let's say you tried x equals 1, you tried x equals 2, and you made your way down to x equals 3, and you subbed in f of 3 into this new polynomial, and you found out that that was 0. Therefore, x minus 3 is a factor. So here we could do the same thing. You could do long division. you'd have x minus 3 on the outside, and under the division statement you'd have your new smaller cubic. But instead we're going to practice our synthetic division. Synthetic division. And again, you can choose whichever method you want when you're doing your own problems. You set it up with a little grid. Because the factor is x minus 3, you put the 0 on the outside here. And then all you do is copy the coefficients of each term. So the coefficient of our x cubed term is 1. Of our x squared term is -4. X term is -3. And a constant is 18. And now if you remember, we're going to pull down the first coefficient because we are always adding down the columns, and then we're multiplying the diagonal. So now in order to get this term, you have to do 3 times 1, which is 3. Then we're going to add down. So you've got -4 plus 3, which is -1. Then you're going to multiply 3 times -1, which is going to get us -3. We're going to add down. So you get -3 plus -3, which is -6. You're going to multiply 3 times -6, which gets you -18. And then we're going to finish by adding down, which gets us a remainder of 0. Now these values that came out become the coefficients of the new polynomial, of the result of our division here. So that means our factors from this set, we've got, and maybe I can just write the corresponding statement. So I'm going to take this cubic, x cubed minus 4x squared minus 3x plus 18, that already has a factor divided out of it, is equal to x minus 3, which is the factor that we found using the factor theorem, times, and here, because we were dealing with a cubic, each of these terms, each of these coefficients belongs to an x term that is 1 degree less than what we started with. So now we're in a quadratic. We've got x squared minus x minus 6. And now since we have a quadratic, the last factor can be done through sum and product. Two values that multiply to -6 and add to -1 is going to be x minus 3, x minus 2. And that was the cubic, that's not the whole thing. So we want to go back up to our value, f of x. So f of x was our original polynomial up here, which says x to the power of 4 minus 5x cubed plus x squared plus 21x minus 18 can be written as, in factored form, make sure you keep all your factors. The first one we found was x minus 1. Then we found x minus 3. And now down here I can just copy down the rest of it, x minus 3 and x minus 2. And if I wanted to simplify that, I notice that there's a 0 in there that's repeated. So we'd have x minus 1 times x minus 2 times x minus 3 squared, so in order 2, which gives us the x-ints of the original function still. So the x-ints are negative, oh, I made a mistake up here. This is supposed to be x plus 2. Sorry about that, x minus 3, x plus 2 to get this. So plus sign here, plus sign here. So the x-ints are -2, 1, and 3. If you want to, you can say that this is an order 2, just to help you out. That's probably familiar from functions. And that is step 2, just finding the intercepts. Y-intercept was easy. X-intercept, we had to set this function equal to 0 and then factor. So in order to do that, we use the factor theorem to determine our first factor, long division to get the, I don't know what it's called, the quotient, I think. And then to get to divide that further, we used factor theorem again, and then we tried synthetic division, which worked, and then sum and product, and we got all of our factors, which gives us our x-intercepts. Okay, if you're close to the bottom of the page or halfway through a page, you're going to want to start a new page for step 3. Step 3 is determining and classifying critical numbers. So this is where we want to take the first derivative of f of x, which is 4x to the power of 3 minus 15x squared plus 2x plus 21. And then in order to determine the critical points, we want to set that equal to 0. And solve for the values of x that make that true. In order to do that, that means we're going to be factoring this polynomial again in order to find its zeros. Again, it's a cubic. It's pretty complicated. There are no common factors. So we're looking at using the factor theorem to find our first factor. In order to do that, we're going to test all the factors of 21. So you might test 1, you might test 3. If you tested 3, I'm just going to do this shorthand, guys. Factor theorem test x equals 3. You find out that f prime of 3 does equal 0. Therefore, x minus 3 is a factor. Then use long division or synthetic division. And you find out that the factors, and then after that you can do sum and product or factor by grouping. I'll write that too. Then use sum and product or factor by grouping. Hopefully you remember all that stuff. And you end up with 0 equals x plus 1, 4x minus 7, and x minus 3, which tells us that our critical numbers are -1, 7 over 4, which is 1.75, and +3. Now to classify those things as a max or a min, we need our second derivative. So classify using second derivative. In order to do that, we're going to find our second derivative, f double prime of x. So we go back up here. We have 12x squared minus 30x plus 2. And we're going to find out what the value is at x equals -1. So for x equals -1, f double prime of -1. That's -1 squared is +1. That's +12 plus 30 plus 2. So that's 44. It's positive. Therefore, and the first derivative is 0 at this point. That's how we got it as a critical point. So it's a critical point that has a second derivative that is positive. Therefore, it is a local min. Let's just go through that one more time. At x equals -1, the first derivative is 0. That means slope is 0 at that point. And because the second derivative is positive, it's concave up. So that's what it looks like right here at x equals -1. Okay. Looking at x equals 1.75. We know the first derivative is 0. The second derivative, again, you'd plug in 1.75 into the second derivative function, which we got right up here. You would end up with -13.75. Because it is negative, we have a local max. So again, the slope is 0. Second derivative is negative, which means we're looking at concave down. So this is what's happening at x equals 1.75. For x equals 3, sub it into our second derivative. We end up with 20, which is positive, which means it's going to be concave up. So we have a local min. The one thing we're missing here is the y-coordinate in order to get our critical points so that we know exactly where to draw these things. So I'm going to do that over here off to the side. I'm just going to sub these values into the original f of x. Okay? So the value of the function when x equals -1 is +1, -1 times -5 is going to be +5, so you look at +6, +7, -21, -18. So this first point is going to be, the value is -32, so the critical point is -1, -32. Then when we sub in 1.75 into the original equation, I'm not going to do all the work here. You guys can do that on your calculators when you need to. 4.4. So that critical point is 1.75, 4.4. And our last one, if we sub in 3 into the original function, we get 0. Therefore, 3, 0 is a local minimum. And that makes perfect sense because back in the first part of the problem, we found out that 3 was a 0 of order 2. So now we know it's a minimum, and the function is going to pop back up at that point. Okay, there are our max and mins. The only thing we're missing is our exact places of points of inflection. Step 4, determine points of inflection. I copied down my second derivative again because points of inflection occur where the second derivative equals 0. So I'm going to find the values of x that will solve this equation. I see all the terms on the right here have a common factor of 2, so I'm going to divide them all by 2. We get 6x squared minus 15x plus 1. And then I could try to factor this by sum and product or by factoring by grouping. but it's not factorable across the whole numbers, across the integers. So we actually need to use quadratic formula. Negative b, plus or minus, square root of b squared, minus 4ac over 2a over 2a. And then just sub in what I know. Negative b is positive 15, plus or minus b squared. I'll just write it out first. 15 squared is 225, but minus 4ac, it's 4 times 6 times 1, all over 2 times 6. Simplify this as much as we can with or without the calculator. We get 15 plus or minus, and then under the square root here, the discriminant becomes 201, and we're over 12. From here, you put it in your calculator twice. You have 15 plus radical 201, then divided by 12, and you have 15 minus square root of 201 divided by radical 12. Divided by 12. So we end up with x equals approximately 0.07 and, or x equals approximately 2.43. Okay, these are the solutions to the equation of the second derivative set equal to 0, which means that these are possible points of inflection. Possible points of inflection. So we need to check for a sign change at each one. So does the second derivative have a sign change at x equals 0.07? So we're going to test one value to the left of 0.07, find out what the sign is, and we're going to test one value to the right of 0.007 and see what the sign is there. So when I put 0 into this this function, okay, we end up getting the value of 2, which is positive. And then when I put 1 in, we get a value of negative 16, which is negative. So there is a sign change. So this is a point of inflection. Therefore, point of inflection at x equals 0.07. And what about our next one? We're going to take the second derivative of a point. We're going to take the value of the second derivative just to the left of 2.4, let's say 2, and just to the right of 2.4, let's say 3. The value of the second derivative at x equals 2 is negative 10, so it's negative. And at 3, it is 20, that's positive. Therefore, there is a sign change, so there is a point of inflection at x equals 2.43. Okay, in order to determine the intervals of increase and decrease and the intervals of concavity of the function, we're going to make this whole table, this summary table of what's happening at every part. We have split the domain of the original function into a few different pieces, and we have identified the points of inflection. So this is what this is going to look like. We've got to consider what's happening to the left of negative 1, consider what's happening at negative 1, and then we had critical points of negative 1 and 3, but we also have a point of inflection in here. We have another critical point at 1.75, so we're going to go from negative 1 to 1.75. We're going to find out what happens at 1.75. The intervals come from the first derivative. The zeros of the first derivative become your critical points. which are the max and mins, which split up the curve into the intervals that are worth discussing. So then we're looking for x is greater than 1.75 but less than 3. We're looking at what happens at x equals 3, and then what happens when x is greater than 3. Picking a test value for each of these. Test value. We're actually going to use values as much as possible, values that we've already determined the value of the first or second derivative for. Okay, over here we're going to use x equals -2. So typo in your textbook. Here, test value is obviously x equals -1. Here, we're going to use x equals 0. Here, we're going to use, obviously, x equals 1.7. Here, we're going to use x equals 2, then x equals 3, then x equals 4. The sign of the first derivative is going to tell us whether the slope of the curve at that point is increasing, decreasing, or 0. Okay? So the sign when we take the value of the first derivative at -2, again, if you needed to do more work, which we kind of do, so you would have space around your chart or whatever, and you would just say, okay, well, I need the value of the first derivative at x equals -2. You'd sub in -2 into the function for the first derivative, and you'd end up with -3. That tells you that it's negative. Then you have the value of the first derivative at x equals -1. We know that's 0. And I might even just go through the chart and put in all my zeros. That's how we got these critical points, right? Those values, the first derivative is 0 at those values. Then in this interval, we said our test value was going to be 0. So I would maybe have to sub that in. If I did that, I'd find out that the value of the first derivative function is 9, which is positive. Then my test value of 2, sub that in. And we get -3, which is negative. Then a test value of 4. If I sub that in, I get a positive value. I don't know what it is because I picked a different number than the textbook, but it is positive, so I'm going to put positive in there. Okay, that gives us our intervals of increasing and decreasing. Now we want to know where it's concave up and concave down. So in order to do that, we're looking at f double prime of x. So another typo in your textbook there. The second derivative of x, the value of it at x equals -2, is it positive or negative? And again, I would go through all of these things again if I didn't already do them. And I would say, okay, take the second derivative, sub in -2, and I'd find out that's 110. It's positive. Here, I'd sub in x equals -1 to my second derivative function. We would find out that it's positive. In between this interval, so sorry, I'll put positive here first. In this interval, we determined there was a point of inflection. Point of inflection at x equals 0.07. And maybe we could go ahead and do our other one too. We said there was a point of inflection at x equals 2.43. At x equals negative 7.5, this is pretty easy. We already determined there was a change of sign for our second derivative. So that means that's going to be negative and this is going to be positive. And then I might still want to sub in to my second derivative the value of x equals 3 to figure out what's happening there. Or sorry, x equals 4. Should be x equals 4. That's my test value. And I find out that it is positive. So positive. All right, this is going to make it pretty easy as we're looking now at the original function f of x, what's happening. So here it is decreasing and concave up. So it's looking like that. Here it is 0 and it's concave up. So that is a local min at x equals negative 1. Here we have a point of inflection. It's going from positive to negative, so it's going from concave up to concave down. There's our point of inflection. There's our min. Here we have a maximum because it's concave down. It's right there. Here we have a point of inflection. It's going from concave down to concave up. From concave down to concave up, point of inflection. Here it's 0, so we have a local max or min. It's concave up, so it's a local min. And here we have increasing and concave up. Last step. You can do it. If you have graph paper, that'll be helpful. If not, no big deal. Our function is going to look something like this. I'm going to stretch the domain. I'm going to stretch my x-axis. 2, 3, 4, 5, good enough. -1, -2, -3, good enough. And down here into negative land, we're going to go by tens. So we got -10, -20. Same going positive, you've got 10, 20, 30. And I'm just going to put my points on here because we already found all of this information. So we have a critical point, our first local minimum at x equals -1. And we found out that that was a critical point of -1, -32. So we're at -1, and I guess I can stretch this guy one more. There's -30. So we're at -1, -32. That's right about there. That's a local minimum. I'm going to put my coordinates. Then we have a local maximum at 1.75. And we found out that that was 1.75, 4.4. So that's right about there. 1.75, 4.4. Then we had a local minimum at 3, 0. And that was order 2, so we know it's going to pop up. That 0 is order 2, so it's going to pop back up again here. What else did we find out? We found out the intercepts really early on. We found out that the y-intercept was -18. So that's right there. We found out that the x-intercepts are -2, 1, and 3. -2 right there, 1 right there, and 3 we already have. That's going to be a bump up, a minimum. What else do we have? We have points of inflection. We have a point of inflection at 0.07. 0.07. And I don't know exactly where that's going to be, but for coming up, it's going to be right about here. and a point of inflection at 2.43, which is going to be right about there. We could find out the corresponding y values of those points of inflection as well to be like super duper ooper accurate. But anyways, here we go. I've got a max here, minimum, sorry, here. It's going to probably be a bit wider. And I've got to come up to my y-intercept, then a point of inflection, so I can have a clear change from being concave up to concave down. It's going to come through x equals 1, reach its max at 1.75. As it's coming back down, it hits that point of inflection from being concave down to being concave up, touches the x-axis at x equals 3, and then carries on upward, increasing. On the left tail here, all I need to do is make sure that I come down through -2 and that it looks reasonable. Da-da-da! Mark my y-intercept, x-intercepts, local max, local min, and the most beautiful sketch of a parabola that you've ever done without Desmos. Practice problems that you should be able to do come from page 192. Page 192, numbers 1 through 14.